All right, let's get out the oscilloscope. We're going to use this to take a look at the AC power supply. This is the DSO-150. You may need to do some mechanical assembly, bolting the case together. I'm using one here that's already put together. Has been bolted together. If the assembly causes any trouble, please reach out and let me know. We're going to also need a power supply for the oscilloscope. Yours may possibly look a little bit different. Just go ahead and get it plugged in. The wall outlet. It's a 9-volt power supply. Do not use the 12-volt supply. That came, the AC adapter. Don't use this one because that is the wrong voltage and it's AC. That's for the rack power supply. So with that in there, you should be able to just power it on. And then you can take the probes that came. And I think we'll start off today using this probe, which has a little hook that retracts and another cable for ground. We're not going to use the ground right away because this scope has a neat feature, which is it has a 1 kilohertz square waveform that comes out on this tab here. And the ground of the cable is already connected because we're using the scope itself to make this signal. So all we have to do is hook up somehow, there we go, the probe on the center pin to the input. So signal is being generated here and then being read on this port. So this is a self-check for the oscilloscope. A few things about oscilloscopes. We're using them quite a bit in this class, almost as much as multimeters. This axis, the horizontal axis, is time. This axis, the vertical axis, is voltage. So it gives us volts versus time. So as it moves across the screen, you're seeing a voltage go up and down. The only real way to get good at using a scope is to play with it. And says what's nice about these is they come with this built-in function we can look at. The volt per division is the relative amplitude. So as I use the adjust knob, turning it, after I hit volts per division, it will change the amplitude, or if I hit that button again, as you see, it'll allow me to move the center of the waveform up and down for viewing. So get used to doing that a bit. So as volts per division is the vertical scale. Seconds per division is the horizontal scale. Let's press that button, and you'll see that whereas volts per division, the fact that we're at 5 volts per division, 2 volts per division, 1 volt per division, etc., is highlighted. When I hit the second per division, the time base is lit up, and I can zoom out and zoom in. And notice the time per division changes: 2 milliseconds, 1 millisecond per division, half a millisecond, etc. Okay, let's look a little bit more at the numbers here, what they mean. So it says 5 volts per division. That means that 1 square, that is just 1 square on the meter, is 5 volts. So if I change it to 2 volts, you'll notice that I have or 1 volt, move it up to put the base right on a line. 1, 2, 3, and a little bit. Again, 1, 2, 3, call it in a third, or 3.3 volts from the base to the top. I can move that around, but you'll see no matter what scale I have it on, it's always that same amplitude. If it's on 2 volts version, I have 2 2/3, which again is about 2 2/3 division times 2 volts is about 3.3 volts. If I'm the 5 volt scale, notice it doesn't quite go to 5 volts, so it gets like about 3 volts, you can see. But you have to look at this number to know what 1 square means. Same for time. Currently I'm at a half millisecond per division. If I make that 1 millisecond, and I hit the button again, I can slide the waveform around. If I look in 1 millisecond, say starting at the middle here, goes up, down, ready to start going up again in 1 square. So that's 1 millisecond per division, which would be 1 kilohertz. I'll repeat that on a different time scale. Here I have 1, 2 divisions for the waveform to repeat itself. 2 divisions times half a millisecond is 1 millisecond period. So I'll write out how that works. 0.5 millisecond per division times 2 divisions equals 1 millisecond, and that's the period. Of course, frequency is 1 over the period. Remember, capital T is the symbol we often use for period. And 1 over 1 millisecond is 1 over 10 minus 3 seconds, which is 10 to the 3, 1 over second. And of course, 1 over second is the unit that we call a hertz, and 10 to the 3 is a kilo, so that would be 1 kilohertz frequency. And that is, of course, exactly what it says on the scope. This is a 1 kilohertz square wave. It's indicated right there. Notice this other switch that's nearby, and I haven't told you about this switch yet. It says AC, DC, or ground. Currently I'm on DC. Someone might say, oh, this is an AC waveform. That's true. And when I change it, you'll find that the AC waveform always changes the level of an alternating waveform. Where if I switch it all the way over to ground, so I switch it all the way this way to ground, now I see nothing. What ground does is it takes the ground of the scope and runs it out and connects it to the input, regardless of what's actually physically connected. So you're reading the ground, and that's at 0. This tells you where the 0 voltage line is. You can see the yellow dot over here. So that's true 0 volts with respect to ground. When I go to the DC reading, that's 0 volts, and it goes up to 3.3 volts, back down to 0 volts. AC, I get a somewhat misleading reading. Notice how it's always centered around the middle of an oscillating waveform. We'll talk about AC versus DC waveforms later. Final button we haven't played with is the trigger. The trigger level is determined by this green dot over here. And we'll delay a more lengthy discussion of triggering for later, but suffice it to say that if I take the trigger